Evaluate integral 0 to infinity cos mx by x square plus a square the whole square into dx where a greater than 0. So this is the given integral is integral 0 to infinity cos mx by x square plus a square the whole square into dx where a is greater than 0. So the given integral having the limit 0 to infinity and the given integral function have the trigonometrical terms. Therefore this is contour integral of type 3. So in this type consider an upper half circle C such that C is minus r to plus r plus gamma. That is, from the diagram you consider this is y axis, this is x axis. X axis is a real axis, y axis is the imaginary axis. An upper half circle, this is upper half circle. Okay, minus r to plus r. So what is C here? C is minus r to plus r plus gamma. The curved region you take it as gamma. Okay, so C is minus r to plus r and gamma. So this is C. So from the diagram the integral can be written as integral over C f of z dz. It represents entire half circle. It is minus r to plus r, minus r to plus r, but the minus r to plus r lies only in the x axis, so that you have to write f of x dx plus gamma, integral over gamma f of z dz. Okay, so by Jordan lemma, as r tends to infinity, integral over gamma f of z dz equal to 0. This is by Jordan lemma. So substituting here, as r tends to infinity, minus infinity to plus infinity, this integral becomes 0. This is only will give. Okay, so now integral minus infinity to plus infinity f of x dx is equal to, as r tends to infinity, this 0, only this integral over C f of z dz. Okay, here integral minus infinity to plus infinity f of x is a given function cos mx by x square plus a square the whole square into dx is equal to integral over C f of z. F of z is convert in terms of z, so cos mz divided by z square plus a square the whole square into dz. And now this cos mz is a real part of e power I mz. So real part of e power I mz by z square plus a square the whole square into dz. Now I can apply Cauchy residues theorem. So what is Cauchy residues theorem? Cauchy residues theorem is integral over C f of z dz equal to 2 pi I into sum of the residues of f of z. Okay, so this is Cauchy residues theorem. Here I am going to apply Cauchy residues theorem. It is real part of integral over C f of z dz. This is 2 pi I into sum of the residues of f of z. Take this is equation number 1, where f of z is equal to, this is f of z, e power I m z divided by z square plus a square the whole square. Okay, now I want to find out the residue for f of z. To find the residues, I want to find out the poles. By equating the denominator to 0, we can find the poles. So put the denominator equal to 0. z square plus a square the whole square equal to 0, which implies that z square plus a square equal to 0, which implies z square equal to minus a square. So z equal to plus or minus ia. Z equal to plus or minus ia. There are two poles, but the poles are multipole, double pole. Why? Because the denominator term having the power 2. Therefore, ia and minus ia are multipole of order 2, or we can say double pole. Okay, so there are two double poles, but you see from the diagram all the positive value or positive imaginary values are lies inside the circle C, negative imaginary values are lies outside the circle C. Therefore here ia only lies inside the circle C, but minus ia lies outside the circle C. But very important thing, both the poles are multipole of order 2. Okay, now this is the formula for residue for the multipole of order m. Here z equal to, if consider z equal to a is a multipole of order m. But here in this problem we found pole ia is a multipole of order 2. Therefore in this problem m is equal to 2 because multipole of order 2 and the pole is ia. So that here pole is a. So a is considered to be ia. Okay, so the pole is ia and it is order 2, so m is equal to 2. Substitute here. So residue of f of z at z equal to ia. Ia is a multipole of order 2. Limit z tends to ia d power m minus 1. M is 2. 2 minus 1 1. So only one derivative. D by dz. Are you clear? So order m means m minus 1 derivative. Order 2 means 1 derivative of z minus a. A is ia. The whole power 2. M is 2 into f of z. What is f of z here? F of z is e power I m z by z square plus a square the whole square. Okay, so next I want to simplify. The simplification is limit z tends to ia d by dz of z minus ia the whole square into e power im z divided by, this term can be split into two parts, z plus ia into z minus ia, but the power is 2, so z plus ia the whole square into z minus ia the whole square, and cancel this and this. So remaining term I want to differentiate with respect to z. So limit z tends to ia. So differentiate by u by v method. What is u by v method? V into differential of u, e power im as the differential, e power im z into im minus u into differential of denominator x square differential 2x, so 2 into z plus ia by denominator whole square z plus ia the whole power 2 so 4. So this is differential, u by v differential over, what is u by v? U, this is v du minus u dv by v square, square of square 4. Okay, now after this limit z tends to ia, one z plus ia can be taken outside, cancel with the denominator. So z plus ia into im into e power im z minus 2 into e power im z, already we took one z plus ia outside and with cancel with the denominator, so z plus ia the whole power 3. Okay, so now I am going to put ia for z. So substitute ia plus ia 2ia, and here im, and here substitute ia. So I into I square minus e power minus a into m ma minus 2 into e power, substitute ia for z, I into I square minus 1 and a into m ma by substitute ia plus ia 2ia, so 2ia the whole cube. Okay, so now next I am going to simplify. The simplification part, you see you can take common term outside. What are the common term here? 2 and e power minus ma. So take outside. So I into I square minus 1. So minus ma, a into m, ma, I square minus and minus. Here 2 into e power minus I, ma, take outside. So minus 2 into e power minus ma, take outside. Whole divided by 2 cube is 8. I cube, what is I cube? I cube is I square into I. I square is minus 1. Minus 1 into I, minus I. So this is minus I into a cube. Okay. So what are the remaining terms? 2 can be cancelled with 4. This is ma plus 1 into e power minus ma divided by, cancel with 2, 4. Already minus also cancel. So 4i into a cube. Okay. So this is the residue for f of z for the pole ia. Okay, so now this residue I am going to substitute in the first equation because only one pole lies inside the circle C. So corresponding residue is this. I am going to substitute in the first equation. Okay, so the formula is the real part of 2 pi I into sum of the residues is only one residue. What is the residue? ma plus 1 into e power minus ma by 4i into a cube. Okay, so I cancel. So after cancelling I, there is no imaginary term, only real term. So collecting the real term, we are getting the answer. So I cancel, 2 cancel, so pi by 2 into a cube of ma plus 1 into e power minus ma. Okay, so this is the value, this is the answer of the problem, but the question is we want to find out 0 to infinity. So here cos mx is a even function, denominator also even function. So this even function can be written as 2 times of 0 to infinity cos mx by x square plus a square the whole square into dx is equal to pi by 2a cube into ma plus 1 into e power minus ma. Okay, so this 2 can be taken in the right hand side. Finally the answer is integral 0 to infinity cos mx by x square plus a square the whole square into dx is equal to pi by 4a cube into ma plus 1 into e power minus ma. So this is the answer of the problem.